Thank you. Good thing we didn't catch me threatening you on camera. No. All right, so now that we have established why we have a Lakers fan in the classroom, we will continue on. What was the question you had? It was from 4-1. Okay, which particular one? 47. X e to the negative x squared over 8. So f of x is x e to the negative x squared over 8. Negative 1 to 4. So remember back in this section, we were trying to find the maximum values on a closed interval, so we use the closed interval method, right? So what we want to do is we want to take our derivative, set it equal to 0, figure out where it's undefined, if it even is. So I take my derivative. To do that, it's going to require some product rule and some chain rule, right? So here's my product. Derivative of the first one is 1 times the second one. And then plus, now the derivative of e to the negative x squared over 8, well, derivative of e to anything is itself. Then chain rule says take the derivative of what's up here. Now remember, negative x squared over 8 is the same as negative 1/8 x squared. Those are the same expressions, right? And then, is that where you, yes? Did you do quotient rule or something on it? Okay, you could. I would avoid that because you get into some trouble with that. Rewriting negative x squared over 8 as this will make your life much easier. Because now it's just power rule. 2 comes out. 2 times negative 1/8 is negative 1/4 x. And then you have to finish off the product rule, which means you need to bring that x out here and put it here. And now I'll clean things up, but I'm going to notice that both of these terms have that e in there. So I'm going to pull that out, factor that out. And what that would have left me is the 1 here, and then these two together, which would have given me negative 1/4 x squared. Set each of those equal to 0, right? Set each of those equal to 0. So e to the negative x squared over 8 equals 0, and then the other one, 1 minus 1/4 x squared equals 0. So can this ever be 0? E to any power cannot be 0. Not going to happen. What does the function of e to something look like? It's the exponential graph, right? It doesn't ever cross the x-axis. As long as we don't move it up and down, which we haven't because we haven't added any numbers out here. So that's not going to happen. Over here, this is going to turn out to be x squared is 4, so x is plus or minus 2. And then, do these answers live inside this interval? One of them does, right, at 2? So I actually throw out the negative, just 2. Questions? Is the derivative ever 0? Is this derivative ever 0? I'm sorry, ever 0, undefined. Is the derivative ever undefined? So go back to your derivative. I like this version of the derivative right here. A little cleaned up. This is a polynomial function. It's defined everywhere. Times, we already said e to anything. This is defined. So this is a nice, well-behaved function. I never have to worry about it being undefined. Nope. Okay. So all I need to do now is plug in the endpoints of the interval, which were negative 1 and 4, and then plug in the only other critical number I had, which was 2. Plug those into the original function. The biggest one is my max, the smallest is my min. So if I plug these in to the original function, it'll be x, so -1, e to the negative x squared over 8. So something like negative e to the -1/8 would be one answer. Then you plug in 4, so 4 e to the -4 squared over 8. I'm just finishing this off. This is 4e to what power here? -2. And then the last one would be 2, then e to the -2 squared over 8. So 2e to the -1/2. And you could probably plug all those into your calculator and figure out which is the biggest and smallest. I don't know. I can't really tell. Only one of these is negative. So this is going to be your min, because that's the only negative answer you get. And then your max, I want to say this one's the max. Someone else can check it. Yeah, that's the max. This number is bigger than 4e to the -2. All right. I think you found the issue. All right. And now that everybody's here, wow. Did you all ride the same bus or what? Okay. All right. Oh, now that everyone's here, I'm going to give you a handout on Wednesday. That's going to state basically that we are having the exam, our next exam, on Wednesday, the day before Thanksgiving. But because I do know some people will possibly be traveling, I will give people the option to take the test on the following Monday or Tuesday. But you have to sign up for it, and I need to know it. I need to have a head count and everything else. So you're going to have to commit to that. I'll give you the handout on Wednesday. You'll circle your option. You'll give it back to me, and then we go from there. Okay. Now I don't want everyone to oh, we're all going to take it after, because that's not the point. I want you to take it before. But if you have a legitimate reason that you can't be here, that's fine. It'll cover whatever we get through this week. I think is, probably most of the rest of this chapter 4. What? This was asked homework from 4-1. It was number 47. Any other homework questions? No? Nobody has homework questions. So what did y'all do for homework out of 4-3? Did y'all do anything? 4-3? No? Okay, y'all didn't do anything out of 4-3? Okay. The 4-2, the mean value theorem. All right, we need to hit 4-3 pretty hard then today. All right, so let's get down to business. 4-3. We had already started this last class with the pictures, so I want to get down to the definitions and just start working some problems. So what does the first derivative tell us about a function? First derivative tells us where f is increasing and decreasing. And what is it about the derivative that tells us that? If the derivative is what, it's increasing. So if the derivative is positive, then f is increasing. If f is negative, then if the derivative, I forgot my derivative mark. If the derivative is positive, then then the function is going up. If the derivative is negative, then the function is decreasing. Those are major results for us. We need to realize that. And then we have something called the first derivative test. So this is how we can apply that to testing functions. Suppose C is a critical number of f. What does it mean for C to be a critical number? If I say C is a critical number of a function, what did it mean to be a critical number? Yes, this means the derivative at C is 0 or the derivative at C does not exist. For C to be a critical number, it means that that's a place where the derivative is 0 or does not exist. Okay, suppose that that's true. Suppose C is a place where that happens. Then here's what we have. Result is this. If the derivative is positive, or I should say, if derivative changes from positive to negative, at C, then f of C is a local max. I showed this to you in a picture last class, but now I'm writing it down. So let me try and draw another picture below this so you can really hopefully get an idea of what's going on. Also, we should say something here. This C is a critical number of f. I'm going to put up next to the first derivative test also C is in the domain of f. In other words, your function has to be defined at the point for you to be even using this test. All right? C must be in the domain of the original function. So take a look at this picture I'm going to draw. I have some function. There's some point C here. And what I can tell you is that at this point C, my derivative is either 0 or doesn't exist. So I'm just going to pick some point here. Let's make it up. And I'm going to tell you right there that the derivative is either 0 or doesn't exist. But also, C is in the domain of the function, which means the graph does exist here. I mean, like, there is a point. It's not a vertical asymptote. It's not missing. It's not a hole. I mean, the graph is defined. This first derivative test says if your derivative goes from positive to negative at C, and what they mean is as you move from left to right, if you go from a positive derivative to a negative derivative, then you have to be at a local maximum, don't you? So it would be like your graph is going up, and then it has to come down. So the only possibility is that that's a local max. Now it could look like this, but it could have also been something more like this. I'll just draw one next to it so you can get the idea. I could have had this. I could have had a cusp, right? So this would be an example where at C my derivative would have been what? 0, but then as I move from left to right, the derivative goes from positive to negative. Here, my derivative would what? Not exist, but my function is defined, and I go from positive to negative, so I have a local max. And in either case, I get local max, right? Questions? All right, now, what do you think the second thing on the first derivative test says? That's right. That's right. So what do you think it'll say? This one said if f changes from positive to negative, vice versa. So if f prime, right? Did I put prime on the other one? Yeah. If the derivative changes from negative to positive at C, then f of C is a local minimum. Picture of this. At C we're defined. We have some point. This time it's decreasing, then increasing. Or if you wanted to do it, you could do it with a cusp. You could go decrease, cusp it, and go increase. Both of those would be local mins, right? Going from decreasing to increasing, going from a slope being negative to positive. All right, example time. Right? Don't you think it's time to do an example? Find local max, min and max. Also find intervals where f is increasing and decreasing. So I'm going to give you a function. Not only do I want to know where all the little local peaks and valleys are on this function, I want you to tell me everywhere that it's going up and everywhere it's going down. Right? So where's the function going up? Where is it coming down? So here's the function. X cubed minus 2, make it 3x squared plus 1. See, notice there's no interval here, right? Not giving you an interval and saying, oh, find the max and min inside this interval. Saying, no, on this graph, tell me where all the lowest and highest points are locally, and then just tell me where it's going up and where it's going down. So what I'm going to need to do is apply the first derivative test, which means, first of all, I need to know where all the critical numbers are. So where are the critical numbers? So I'm going to find the critical numbers first. To do that, I take the derivative, which is 3x squared minus 6x, and that's it? Yeah, now we're going to set that to 0, right, to find it, and that's going to be nice. So now I want to know where this derivative is 0. So I set that thing equal to 0. Is that not a nice equation or what? All right. It's a little better than that, like x e to the negative x squared, all that crap, right? This is a little nice little polynomial. Factor out of 3x, left with x minus 2, So where do we have this happening? 0 and 2. So I have two critical numbers, don't I? Two critical numbers? How about anywhere where the derivative is undefined? Or derivative does not exist? Anything? Derivative is a nice polynomial, right? No issues? But I at least paid attention to the fact that I didn't need to think about it. Okay, so what does the first derivative test again say? It says that if C is a critical number, I actually have two C's, don't I? 0 and 2. If C is a critical number and the derivative changes from positive to negative at C, then I've got a local max. If it changes from negative to positive, I got a local min. How am I going to check to see if it changes from positive to negative? Do you see what I'm getting at? Like, I don't know what's going on, do I? Necessarily? I mean, I know what the derivative is doing here, right? Because it's, yes, we won't always know that though. But yes, in this case, yes, we do kind of know the shape. So look, let's just try something, all right? Let's plug in, let's test some points. But here's the way I like to approach it. Here's what I've got so far. I know that at 0 and at 2, my derivatives are 0, right? So I'm going to use that. These are not vertical asymptotes, okay? What I'm doing is I am partitioning my number line into 3 sections. I have everything to the left of 0, everything in between 0 and 2, and everything to the right of 2. My question is, what is the function doing in each of those sections? I know what's happening at 0 and 2. At 0 and 2, the derivative is 0, right? I have a flat tangent line, but I don't know what's happening to the left and right. So now what I do is I pick test points. I'm going to pick something here, pick something here, pick something here. What do I pick? Anything you want. It just needs to be in the domain of the original function, okay? Which our original function was what? X cubed is defined everywhere. Any points I want. So how about -1? That sound good? I'm going to circle it. Also notice, I always like to put little X's here and circle the numbers so I don't confuse these with where they were actually 0. Like 0 and 2 are my two critical numbers. This is a test point. Right here, something in between 0 and 2. 1. Could you have picked 1.2753? Sure. Something to the right of 3? Pi? But, I mean, why? Just pick 3, right? I mean, you could do it, but pick nice numbers, because guess what you get to do with these? Plug them back in. Where? Derivative? I'm hearing two things. Derivative and original. What makes more sense to you? That's what we have to be careful with. Look at, what does this say? If the derivative changes from positive to negative. If what changes? The derivative. I want to know what's happening to the derivative, right? What the derivative does will tell me what the original function is doing as far as going up and down. But I need to investigate the derivative. So all that time I was stressing, remember, plug in the endpoints, plug in the critical number into, and I'd always say, where do you plug it in? And everyone would say function, the original function, right? That's closed interval method. Open interval method, you have test points, and those test points always go into the derivative. Always, always, always. All right, so I need to figure out what f prime of -1 is, what f prime of 1 is, and what f prime of 3 is. So I go up here to my derivative, which is right there. Not that. Wow, that kind of looks cool. I like that. I need to plug in -1 into this. Right, that's my derivative. I'm plugging it in. I'm going to see, all I care about is what? If it's positive or negative. That's all I care about, right? Is it going to be positive or negative? If it's positive, it's going up. If it's negative, it's going down. When I say it, I'm talking about the original function, right? Slope of tangent lines, either positive or negative. So plugging -1 into that, I get 3 times -1 squared minus 6 times -1. What do I have there? 9. And 9 is greater than 0, right? It's a positive number, right? So what does that tell me is happening over here? It's rising, it being the original function. So I'm going to put this, watch. F prime is greater than 0, which means F, not F prime, is increasing here. Notice the difference. The derivative being positive over here tells me that the original function is going up over here. Yes? Doesn't what? Good question. Is it possible that this could go up and up? How about if I draw this right here? Look at this point right here on this curve. What's the slope of the tangent line there? 0, right? What's it doing on the left? It's going up. What's it doing on the right? It's going up. It is possible that this could go up, up, and still be 0. In fact, it might actually do that. Has anyone tested 1? 3 times 1 squared minus 6 times 1, no, it goes down, right? Negative 3? It's less than 0. So I have F prime is negative, which means F is decreasing here. And then 3 times 3 squared minus 6 times 3. It's 9 is greater than 0. So F prime is positive. F must be going up here. That makes sense? Okay. Tell me about local maximums and local minimums. You have to be real careful with the way you say things here. All this stuff I did in red was just the first derivative test, right? It was just to figure out where things were happening. My critical numbers are where I'm actually having these things happen, right? My local max and mins. So tell me about local max. Do I have a local max? Local max is happening at 0 because it goes from up to down, right? So at x is 0, right? But I don't really want to know what the x value is. I want to know what the x and the y value are. Like I want to know that point on the graph. I want to know what the maximum is. So all you have to do is plug 0 into what now? Plug this 0 into the original function. See, this is why things get a little confusing. See, I want to know how high up my point is. If it's the local max, how high is it? We'll plug 0 into the original function, and what do you get? So f of 0, just to stress that I'm plugging it into the original function, and that gave you 1, right? 0, 1 is a local maximum on that function. How about a local minimum? Where's the local min? It happens at 2, right? So I need to plug in 2 into the original function. What happens if you plug 2 into the original function? You get negative 3? Everyone understand where I'm plugging those in? Well, I didn't plug them in, but have we answered everything that was asked? Not yet. I wanted to know where the intervals where it was increasing and decreasing. Intervals where it's increasing and decreasing. I'm going to put that on this page because I don't want to go to a whole new page. That's part of our answer right there. I'm boxing it. The other part, where is F increasing? So look at over here. This is the way I'm going to write this. And this notation is okay with me on a test. If I want to know where F is increasing, you can just draw that, right? That was this, right? Increasing. Where was it increasing? Well, over here, right? But forever over here. Everything to the left of 0. Not to the left of negative 1, to the left of 0. Everything that way. So we say that how? Negative infinity to where? 0. Is that the only place I was increasing? No, over here. And that happens from where? 2 to forever. So we put union between them. Have y'all seen that union symbol? 2 to infinity. Where is f decreasing? In between, so 0 to 2. And, you know, I like color. Especially this projector is really good at color. So those two, well, it kind of messes up what you can see. Right? That's the corresponding, that's what matches, right? Everything between 0 and 2, that's this. Everything to the left of 0, everything to the right of 2, that's this. Yes? Good question. Does it include 0 and 2? It doesn't matter, okay? Here's the reason why. To talk about increasing and decreasing, you have to have 2 points. To say that a function is increasing somewhere means that one point is smaller than the next one, right? Then one point, the next one, you know, to say it's going up, you always have to have 2 to compare to. So even if we include 0, it doesn't matter because we can get as close to 0 as we want and compare it to any other point. It's the same thing. So yes and no. You could, if you put brackets on the 0, that would be fine. It wouldn't be wrong. Okay? Without the brackets, it's still correct. Either way. All right? That's a weird one. It only really works when you're talking about increasing and decreasing, that you have that freedom. All right. Here's something, just this one just popped into my mind. This one, we'll go quick through this one. Same instructions, all right? Same instructions. Find the local max, local min, find where it's increasing, decreasing. Very simple function. F of x equals x cubed. So first, let's start off by taking the derivative. What's the derivative? 3x squared. Now what we're supposed to do is find the critical numbers. So I take that derivative, and I want to know when it's 0, which means I want to know when 3x squared equals 0. Which means I just want to know when x squared is 0, which means I just want to know when x is 0, right? That's it? X is 0. It's our only solution. And then I want to know when the derivative does not exist. Is that going to happen? No, I don't have to worry about that because my derivative is quadratic, no problems. So now what I suggested that you do is that you draw a number line and use the critical numbers to break up your number line. So that's what I'll do. 0. This will break me into what? 2 different pieces there? Yes? Negative 1, 1. Testing those 2 points into the derivative. So I'm going to test those into the derivative. What's the derivative at negative 1? What's the derivative at positive 1? They're the same. It's 3, which means that it's positive, right? So your derivative here is positive. Your derivative here is positive, which means your function is going up, which means your function is going up, right? Do you have a local max or a local min? That's right. So this is going to look exactly what I drew when you asked that question earlier. But the definition of a local max is that you must go from positive to negative. You have to go from positive to negative. And so since we don't have that, we don't have it. Okay? Make sense? So we have no local max. No local min. And what about where the function is increasing and decreasing? Where is it increasing? Where is it decreasing? It's always increasing, isn't it? Now, even though the derivative is 0 here, to the left of it, it's what? Positive, right? I mean, sorry. It's, let me draw the graph. That's the graph, okay? If I'm riding this like a roller coaster from left to right, I'm going up the entire time, right? Even when I get to this point, the tangent line is 0. But as soon as I move to the right of that point, I'm going up again. So I am always going up. That's why I was saying you have to have 2 points to compare increasing. I can't compare whether or not I'm taller than someone else if I don't have another person to compare to, right? So even though my tangent line here at this point is 0, I am an increasing function because when I compare myself to the number to the right of me, I'm smaller than it. And then as I go to the right of that, I'm smaller, right? The one to the right of me is getting bigger. So how do I say it's increasing everywhere? When you say negative infinity to infinity. And then where is it decreasing? Never. How do I say it's decreasing never? It's decreasing on the empty set, which means this is not 0, this is the empty set. Did we talk about that beginning of the semester? Difference between, okay, that means where is it decreasing? It's nowhere. The set of nothing, as opposed to the set of everything, all real numbers. Real quick, this one was going to go super fast. Same questions. How about f of x is 4x? I just want you to see something on this one. It's going to be kind of interesting. It's a lot, yeah, but let's just look at it for a second. What's the derivative of this? Bless you. What's the derivative of this is 4, right? So I'm supposed to find the critical numbers, right? So I'm supposed to set the derivative equal to 0, which means I get 4 is equal to 0, right? That doesn't happen, ever. But wait a minute, I'm supposed to draw a number line, right? And I'm supposed to figure out where the function's increasing, decreasing, right? That's what I was supposed to do, get a critical number and then like break up my number line, right? What's that? Yeah, I don't have any critical numbers. So how am I going to determine if it's increasing or decreasing? Well, but my derivative is not 0. My derivative is never 0, so I know it's not, like the function doesn't flatten out, right? So think about it this way. The critical number tells you where you have changes in your derivative, right? Where it goes from positive to negative. This is telling us there's nowhere where we have a change, which means whatever the derivative is, it stays that way the whole time. So you remember how we would break up our number line and pick test points? Well, you have one section to look at. It's the whole damn thing. So pick a test point. 0? What's f prime of 0? Well, it doesn't matter because what is f prime always? 4, which means that it's positive, which means that your function's increasing, right? Your function, your derivative is always positive here, so your function is increasing. Does that make sense? What does the graph look like? 4x is a line with slope 4, right? That's always going up. What I'm trying to get you to see in this example is what happens if your derivative doesn't have a solution. You still draw a number line, but now you don't have multiple points to test. You just test one, and whatever that answer is, that's the way it behaves the whole time. Yes? Empty set, yeah. Yeah, f would be increasing, negative infinity to infinity. F would be decreasing on the empty set. Yes, I would accept that also, instead of negative infinity to infinity. No local max, no local min, right? No local max, no local min. Okay, let's look at this. I'm just pulling this problem completely out of the air at random, so I have no idea how this is going to go. All right, so be prepared for this to suck tremendously. I don't know. This looks interesting to me. All right, what is going on here? Where? Same question. Where is it increasing, decreasing, local max, local min? Figure it out. So what's the derivative of this? Well, you're going to have to apply the quotient rule, aren't you? So it's a derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. You agree? Let's clean up that numerator. Well, only if you split it into two fractions. You would have to do this over this and then this over this separately. Can't do it at this point because there's two terms up there. So I'm going to go x squared minus 1. What is this? Minus 2x squared all over x squared minus 1 squared. So what do I have here? What's my numerator there? Negative x squared minus 1 or negative 1 minus x squared, same thing. All over x squared minus 1 squared. That's my derivative right there. I don't think there's a whole lot more I'm going to be able to do with that. I'm going to box it because I'm going to be referring back to it. There's my derivative. Now I'd like to know when it's 0. When is that derivative 0? Well, the only time you ever have to worry about a fraction being 0 is when? When the top is 0. So just set the top equal to 0. And you're going to get something here that's not going to make a whole lot of sense. You're going to get x squared is negative 1. And that's not possible, right? As long as we are not talking about imaginary numbers, which we're not, you're not going to be able to find a solution for this. Right? All I did was move the negative x squared over to the other side to make it positive. So there's no solution here. So I don't have any critical numbers yet. What do I also need to check? Where the derivative is not exist. So look at your derivative. Look at this thing over here. Where is this thing undefined? And 1 and negative 1, right? Because if I plug in 1 into this, I get division by 0. If I plug in negative 1 into this, I get division by 0. So in either case, those are critical numbers. Now, we have to be careful because look at the original function, though. The original function was not defined, right? Look at this. 1 and negative 1 are not in my original domain, are they? Are they? Now, let's just see what happens. Please keep that in mind. Are you all right? Seems like you're thinking about those better days back in the early 90s. No? I'm sorry, man. Sorry. I know. I think it's a respect thing, you know? No, it's not. Okay, so I'm supposed to draw a number line. And I'm going to put these two numbers, but I'm putting them because I know that they're interesting on the graph, but I'm not quite sure what I'm going to determine because of this, all right? And I'm going to pick some test points, and I'm going to plug them into my derivative and see what happens. So I'm plugging -2. I'm going to plug in 0 is a good number between a positive and negative number. Right, whenever I've got 0 in between, I always like to grab it if it's there, because 0 is usually pretty easy to plug in. And I'm plugging these into my derivative, which I'm going to give myself some room back here. So I'm plugging it into this. So first let me try f prime -2. That's going to be -1 minus -2 squared over -2 squared minus 1 squared. Something like that, right? What can you tell me about the denominator? Just overall, it's going to be what? When I'm done with all the operations, it's going to be positive number, right? And it's going to be 9, whatever. But it's going to be positive, right? I can tell that because it's squared at the end, yes? As long as it's not 0, which it's not, it's going to be positive on the bottom. So positive on the bottom. Now tell me what's happening on top. It's going to be -1 and then take away, this is going to be a 4, so it's going to be negative on top. So I can tell you right now that a negative divided by a positive is negative. So I don't even care about this, like what the number is. That tells me over here to the left of -1, my original function is going down, doesn't it? Now what's happening at 0? You get negative again, right? It's a negative on top, positive on the bottom. It's negative. So that means my original function is going down here. What about 2? I'm not going to show it, but if I plug in 2, it's going to go down again, right? Yes? Now I'll ask you the same question I asked earlier. Do I have a local max or min? No, because I don't have a change, right? Where is it decreasing? Seems like everywhere. But why can't you say everywhere this time? Because your original function is not defined at -1 and 1. So you can't now say that those are part of its domain, like it's included in there. So you're actually going to have to exclude these two numbers. So the way you would say this is this. F is decreasing on -infinity to -1, union -1 to 1, union 1 to infinity. See, you have to tell me where it's going down, but you can't not include places that aren't there. Where is it going up? Empty set. That's still okay. But something a little bit more subtle that I want to make sure I point out here. And you know what? I think I'll do it on another example. All right, but I'm going to illustrate, I guess, just by warning you, all right, on this problem. What if, okay, this is a big if. What if in this middle piece we would have come up with that the function was increasing here? Would you have a local minimum and a local maximum? Well, I said that if you go down then up, it's a local max, right? But that this would have to be a critical number, and that number has to be in the original domain of the function. This -1 is not in the domain of the function, which means that you have a hole or an asymptote there. which means you cannot have a local max or a local min there. Now that didn't happen, but let me give you an example of one that does, and that way you can really see it come to life, all right? I hope. What if we did this? Same instructions. F of x equals, we'll keep it relatively simple, 1 over x. So I take my derivative here. My derivative is negative 1 over x squared. I just did that by just rewriting this as x to the negative 1 and then doing a quick power rule instead of doing all that quotient rule stuff. Quick power rule gave me negative 1x to the negative 2, and then I just dropped down the x to the negative 2. So, is that all right? I want to know when the derivative is 0. Well, I want to know when negative 1 over x squared equals 0. The only time I worry about a fraction being 0 is when the top is 0, and that's not going to happen, right? So I have no critical numbers that give me that the derivative is 0. How about where the derivative does not exist? X equals 0, right? I can't have division by 0, but keep in mind, this is not in the domain of the original function, is it? It's not in our domain of our original function. You can't plug a 0 into the original one. You also can't plug 0 into the derivative. But it's still going to help me in partitioning up my number line. Are there any questions? I know I'm working a little bit faster through this one, but I'm trying to get to the point here. Here's my number line. Here's my partition at 0. I pick something to the left and to the right. Is it going to matter? Let me see. I'm plugging in negative 1 and 1. What happens when you plug negative 1 into this? Doesn't matter. It's going to get squared, right? So you get negative 1 over a positive number. So it's going to be negative. Crapola, man. Damn it. I'm just pissed off at myself. Same thing's going to happen on the other side. Right? It didn't do what I wanted it to do. What did I want it to do? Go down, then go up. Damn it, I picked the wrong function. I wasn't thinking. That's a brain fart on my part. But you help me try and answer this. Where does this have a local max? Local min? No, no, right? Where is it decreasing? Or where is it increasing? Nowhere. Where is it decreasing? Negative infinity to 0 union 0 infinity. Again, because that 0 cannot be in the domain of the original function, you cannot all of a sudden include it as part of your answers later. That 0 is not allowed in any answer you put in. Understand? Now, let me do the one that I know is going to work, all right? It's Monday. F of x equals 1 over x squared will work. Super quickly, I'm going to move through this one. So you don't even necessarily have to write this if you're okay with the idea of that's your derivative, okay? That's your derivative. The only place I have to worry about is 0. I have my number line, 0. I break it up. I do my test points, negative 1 and 1. If I plug in negative 1, I get a positive number, so that means my function's increasing. If I plug in 1, I get a negative number, it's decreasing. All right? Check this yourself. You do the math yourself. You can figure out what the derivative is. You can set it to 0, figure out where it doesn't exist. It'll go up and down. Now, you see, I'm pointing this out because I want you to see that if a student tells me that there's a local maximum at 0, it's incorrect. Right? It's incorrect. You do not have a local maximum at 0 because 0 is not in the domain of the original function. All right? Now, you can tell me where it's going up and where it's going down. You can tell me f is increasing on negative infinity to 0. You can tell me f is decreasing on 0 to infinity, but you cannot tell me that you have a local max at 0, nor do you have a local min. What does the graph of the original function look like? What does 1 over x squared look like if I were to put it on graphing calculator? It would look like what we call a volcano function. It's like a volcano. Goes up forever on both sides. It's asymptotic. So yes, it goes from increasing, right? And then it goes decreasing. But at 0, undefined. So you can't have a local max there. Set the denominator equal to 0. I'm looking at this and I'm saying, when is this function going to like hate me? And it's basically going to be if I try to plug in 0. So if you want, you could say I'm taking the denominator and I'm setting it to 0 to figure out what makes that happen. All right. Now let's look at the second derivative. Second derivative gives us what's called concavity. The concavity of a function. Remember I talked about concave up as a smile, concave down as a frown? And I need to be clear on that because I think there was a little confusion on it. If f double prime of c equals 0 or f double prime of c does not exist, and f double prime changes from positive to negative at c, or f double prime changes from negative to positive at c, then c is an inflection point, is called an inflection point. Okay, so let me remind you from last class what the second derivative told us. If the second derivative is positive, it means that our graph looks like this. It's part of a smile. Now, this is the part that I think I confused people in class with last time. It can be the left side of that smile or the right side of that smile or both. So you could look like that, or you could look like just this part of it, or you could look like just this part of it. So this would be concave up, but it's the whole smile, right? This would be concave up, but it's just the left part of the smile, and then the last one would be concave up, but just the right side of the smile. Make sense? Then if the second derivative is negative, it's going to be either the entire frown, the left side of the frown, or the right side of the frown. Make sense? Now, what was being stated above this was that if you change from positive to negative, if there's a point where you change from positive to negative, that's where last class I was telling you where like the frown becomes the smile. It's like the corner where the frown becomes the smile. That's called an inflection point. Okay. I think we're good to try something now. Let's say we have something like this. F of x equals 200 plus 8x cubed plus x to the fourth. Find local max, local min, inflection, I'm going to put INF, inflection point, or points, there might be more than one. Intervals where F is increasing. That's the symbol I use for F is increasing, right? Tell me where F is increasing, where F is decreasing, and how am I going to ask you to tell me where F is concave up? I'm going to write F concave up like this, F concave down. We're getting to the point where we're almost going to be able to like draw an entire function without needing a calculator at all, which is the way they used to do it by hand. Because we're going to be able to know where the graph's going up and down, and we're going to be able to know if it looks like a frown or a smile, and then we connect all the points together and we draw it, and we got a good graph. Okay, so everyone understand what I want. Where's the local max and min? Where are the inflection points? Tell me everywhere it's going up, where it's going down, where it's smiling, where it's frowning. All right. I'm going to need derivative. Start with that. What's the first derivative? So 4x cubed, yeah, I'll put it in descending order. 4x cubed plus 24x squared. I need to set that equal to 0 and figure out where it doesn't exist. So where's that derivative 0? Well, I think you can do some factoring on that, can't you? Pull out maybe a 4x squared. Be left with x plus 6 equals 0. Set those each equal to 0, and you get 0 and negative 6, right? So now what I do is I draw a little number line, I break it up, and I do some test points. You're going to get really tired of this really quick, this method, because it's a lot going on here, okay? I mean, you just have to kind of repeat. What should I test? Negative 7, okay. Negative 1 and 1. Notice I'm not being very accurate with where I'm putting these. I mean, I just know it's between there. And I'm plugging those into what? The derivative, right? Now here's my derivative. But I'm going to be kind of smart about this. I'd already factored my derivative down here, didn't I? What do I know this will always be? 4x squared. Positive. So all I really need to do is figure out what x plus 6 would be. Right? So what happens if I plug negative 7 right in here? You get negative, and then times it doesn't matter. This is positive, right? So that would be a negative. So that means, watch, I'm going to stop drawing the f in there. The arrow going down, everyone understands that means the function's going down. What's happening at negative 1? It's positive. Now, at 1, it's positive again, right? So, do I have a local min? Local min? Yes. Now, I'm going to ask myself real quick, was negative 6 in the domain of the original function? Yes, it was a polynomial. So I know this is a nice point on the graph. So I know that I have a local minimum at what? Negative 6, f of negative 6. I'd have to go figure out what that is. All right? I'm not going to do it right now. I don't feel like it. You go plug that in at your own leisure when you're just having fun at home later. Okay? Negative 6 goes in function. I know that that's a local min. What about at 0? Local max? No. So local max, I'm just going to say none, right? I don't have any. I'm not saying empty set. I'm just saying no, I don't have a local max. Okay, where am I increasing? Where is my function increasing? -6 to infinity, right? -6 to infinity. It's okay that I went past 0. I didn't break it up into multiple intervals because 0 is part of my domain, right? It's okay. What about where it's decreasing? -infinity to -6. Beautiful. I've answered almost all the question, right? Everything else that's being asked has to do with the second derivative, right? Everything. So as you're going to see, I'm going to do everything I just did, but on the second derivative instead of the first derivative. So let's take a look at the second derivative. What is the second derivative? F double prime of x would be 12x squared plus 48x. Everyone cool with that? I don't remember what it was. Yeah. That's my second derivative. So I ask myself again, when is it 0? So I can break up my number line again and look at the different places and see where it's, instead of going up and down, where it's smiling and frowning. That's the difference. Instead of saying up and down, it's now smiles and frowns. So when is the second derivative 0? Well, let's factor that, baby. 12x comes out, x plus 2. All right. That's it. No, that's not 2. That's 4. So I get two solutions. X is 0 and -4. How about where the second derivative doesn't exist? It's polynomial. So, I mean, you really don't even have to pay attention to that if it's polynomial to begin with. Here's my number line. -4, 0. I'm plugging in test points. -5, -1, and 1. Where am I plugging those into? The derivative, right? Now this one, when it's factored, doesn't work out as nice because 12x doesn't have to be positive. But I could still do it here, couldn't I? Like what's 12? Let me see, -5. What's 12 times -5? Negative number, right? What's -5 plus 4? Negative number. Negative times negative should be positive, right? So what I'm going to put here is I'm not going to put an arrow going up. I'm saying the second derivative is positive, which means my original function is happy, smiling, right? My original function is smiling in there. When I plug in -1 here, what would happen? Negative, positive. We get a negative, which means my original function is frowning in here. Following this? What part of it? No. I'm looking. No. Look, I'm hearing you, but I said you get it. And she should. Why this is negative? -1 was my test point. I plugged it in right here. Negative. Well, you could do it up here also, but I just find it easier to go right here. That's a -12. -1 plus 4 is 3. So I have -12 times +3, and it's a negative number. And then plugging in 1 to the same thing, you should get positive. So with the second derivative, we don't talk about local max, local min. All we talk about are inflection points. Anywhere where we have a change in concavity, where it goes from positive to negative or negative to positive, we call that an inflection point. But again, the point has to be in the domain. So where do we have inflection points? Inflection points at -4, f of -4. I'm not going to plug that in right now. Where else do we have an inflection point? 0, f of 0. I could probably plug that in. That'd be easy. So I have two inflection points, right? All right, where am I concave up? Where am I concave down? So where is my original function smiling? Where is my original function frowning? That's what I want to know now. Tell me where it's smiling. It's an interval. Negative infinity to negative 4, union 0 to infinity, and then frowning from negative 4 to 0. Are you all following this? I mean, your hand hurt from writing? No? Okay, I want to take a quick little break. I want to share a story just because it's Monday. We're going to do another one of these in a second, but I want to share a story with you I think is kind of cool. I'll pause the video so you don't have to. I think you've had enough fun with polynomials. All the same instructions from the last problem. Figure out where it's local max, local min, increasing, decreasing, inflection points, concave up, concave down, all of it. Well, I'm going to help you out with this one. The ones that I want you to do are going to be for your homework. So I need the derivative. Power rule on both of those. You agree? Okay, we have 10 thirds x to the negative 1/3 minus 10 thirds x to the 2/3. Am I going to need a second derivative later? Can I just get it now? Okay. Second derivative, negative 10/9 x to the negative 4/3 minus 20/9 x to the negative 1/3. So I'm just using power rules on those, right? Now I need to know where the first derivative is undefined, where it's equal to 0. So it's going to be where the algebra is going to start to get a little nasty. All right, where is my first derivative equal to 0? Let me clean it up first. Do you agree that's 10 over 3x to the 1/3 minus 10 over 3x, I'll put the x on top there, x to the 2/3. That's my original derivative. Whenever I have derivatives and I'm going to set them to 0 and start messing with them, I always like to get a common denominator. So I'm going to need to introduce an x to the 1/3 here and here on this second fraction. Multiply by x to the 1/3 here, x to the 1/3 here. Y'all follow? Now I'll have a common denominator. My numerator will be 10 minus 10 again. And then what is x to the 2/3 times x to the 1/3? X to the, careful, you're adding them. So 2/3 and 1/3 is 3/3, so just x. Then all over 3x to the 1/3. Yes. Yeah. I like it. Because I can set that to 0 pretty easily, right? Can you? So now let me get the derivative to 0. 10 minus 10x equals 0, so x must be 1. That's one critical number. What else do I need to check? Where it's undefined. And is it? Where's the derivative undefined? 0, right? At 0. Now, is 0 even in our domain? You can't plug it in here, right? That's the whole problem. You cannot plug it into the derivative. However, look at the original function. 0 to the 2/3 is defined. 0 to the 5/3 is defined. It's part of our graph. So this is the first time I think I've even given you an example of something like this where the derivative being 0 is a point that lives on our graph, and the derivative being undefined is also a point that lives on our graph. Okay? So this is going to break up our number line into 3 sections. 0 and 1. I'm going to have 3 test points. -1, 1/2, 2. Where are those going to go? Where am I plugging them? Derivative, right? And I think I'll take, yeah, right here, this derivative right here. I like that version. Let's plug in -1. -1 up here, it's going to be plus up top, right? Because negative 10 times -1 is positive. So plus up here, and then what do you get down here? -1. What does -1 to the 1/3 mean? Cube root, right? Cube root of -1. Whoa. This is the cube root. So if I plug in -1 into that, the answer is -1. You can take a cube root of a negative number. That's fine. So I should get a negative on the bottom and a positive on top, which means I'm negative. So that means what do you think? Is it better to test negative or positive? Depends on what you're being tested for, right? It's a joke. Better to test positive or negative? Depends, right? That depends. Okay, so what about 1/2? What about 1/2 in there? Up top, 1/2 of 10, it's 5, 10 minus 5 is 5. So you get positive on top. And then what's the cube root of 1/2? Well, it's positive, right? The cube root of 1/2 is some positive number. So we should get positive over positive, which is positive, so it goes up. And then plug in 2. If you plug in 2, you should get negative. Is it okay that I'm leaving that up to you to plug in and convince yourself? Wow, we got a lot going on here. We have a local max, maybe. Do we have a local max? At where? 1/f of 1. And remember, that's because we go from increasing to decreasing at a point that our derivative is 0. Yeah, it's where our derivative is 0, and that number actually can be plugged into our function. So we do have a local max there. How about a local min? At 0/f of 0, and that's because we go from decreasing to increasing, and 0 is in our domain of our function. Now, even though our derivative doesn't exist there, our function does, and that's what we need. So we probably have like a cusp or something here. So it probably comes in something like this. But the function's defined there, so it will constitute a local minimum. It's only when this point can't be plugged into the original function that we have problems, and we can't say it's a local min. All right, where is it going up? Where's my function increasing? 0 to 1. Decreasing, -infinity to 0, union, 0, oh, no. 0, 1 to infinity. All right, we've got local max, local min, increasing, decreasing. Yes? And now the second derivative. We got to go mess with that. Questions? Here's my second derivative. Do you kind of see how this is like the same process, just on a different thing? Like the second derivative, same thing. You're setting equal to 0. We find out where it's undefined. You're still going to test points. So it's very much the same thing, just different function. And in this case, is it going to be easier or harder? Let's see. Let's clean it up first. The second derivative, I'm going to rewrite it. It's negative 10 over 9x to the positive 4/3 minus 20 over 9x to the positive 1/3 I need a common denominator to put these together. What can I use as a common denominator? 9 x to the 4/3. Yeah, how do I turn this into an x to 4/3? I come in with an x to the 3/3, because when I add these together, I get 4/3, right? When we add the exponents. But x to the 3/3 is the same as what? X. I'll leave it there, but let's just all realize I'm really just multiplying top and bottom here by x. So I get negative 10, take away 20, x over my common 9x to the 4/3. When is my second derivative equal to 0? Does everyone realize what I did here? Negative 10, take away 20, that's just x. Then the bottom, same denominators, put them together. Negative 1/2 is what we get from this. So we have something interesting happening at negative 1/2. Where's the second derivative undefined? 0 again, right? We have some problems with division by 0. So at this point, I can draw a number line. Negative 1/2, make sure you get these in the appropriate order, and 0. I'm going to plug in, let's say negative 1, negative 1/4, and 1. And I'm plugging those into this second derivative, right? What does it mean to raise something to the 4/3? Cube root, but then 4th power. So no matter what I plug into the bottom, it's always going to be what? Positive. So it's just a matter of really determining what's happening up here. So plug in negative 1, and what do you get? Positive, which means that I have what happening here? Smile. Okay, concave up there. I plug in negative 1/4. It'll be negative. And I plug in 1, negative again. Is everyone clear that these numbers are being plugged into this? Yes? I'm doing it visually, but if you needed to, you just write the numbers in, try and convince yourself what's happening. Where do we have, if we even have, an inflection point? Do we have inflection point? At negative 1/2, f of negative 1/2. I would expect, again, on your homework, you would actually go plug those in, figure out what they are. I'm just trying to save us time. Is that the only inflection point we have? Yeah, this is the only one because it goes from concave up to concave down. Here it's concave down to concave down. That doesn't change. So if it doesn't have a change, we won't mess with it. Now, where is it concave up? So f is concave up on negative infinity to negative 1/2. F is concave down where? (1/2 to infinity. See, I can skip through 0 because 0 is part of our original domain. We're getting real close to being out of time, but I want to show you this graph. We good? Okay, I want to show this to you. See, was I able to get it to work out on this before, or did I have problems? Yeah, let me try it again. It was 5x to the 2/3. I don't think it worked that way, did it? 1/3, and then raised to. And then we had what? Plus, minus. (5/3). Oh, so 5. Crap, I think this is it. See what we get. Where were our critical points? 0 and 1, and (1/2). I'm still, see, I'm not getting my negative side of this graph. Damn it. Okay, well, I'm not getting the other side of this graph. But what happens here? We have a critical point. Where was our local max? At 1? So you can see we have a local max. We were decreasing to the right of that, increasing from 0 to 1. What we're not getting is the left side of this graph, which is just the limitation of this darn thing. But I'm pretty sure we have a cusp here. Pretty sure what's happening is it's coming down this way like this. What's that? Yeah. I don't know why it doesn't like it. Okay, it's 240. So here's what I think you should do for your homework in this section. Page 222. 1 through 7 odds. And then 25 through 33 odds. Now on these right here, skip part D. Part D on those asks you to use the information to draw a graph. That's what we're going to spend the next class on. How we do put all this information together, just draw a picture. All right. Good day.